Hello and welcome back to the classroom. This is me, Mr. Wong. Today we're going to be covering Module 3, Waves and Thermodynamics. The inquiry question is number 3, sound waves, and we're going to look at 3 specific dot points. We're going to look at conducting a practical investigation to relate pitch and loudness of sound to its wave characteristics, model the behavior of sound in air as a longitudinal wave, and relate the displacement of air molecules to variations in air pressure, or pressure in general. Just before we start, I want to go through how everything in this particular module is linked together. So, as you know, in Module 3, we're talking about waves and thermodynamics, but thermodynamics can come a bit later. With waves, there are 2 types. You have mechanical and you have electromagnetic. Mechanical is for waves that require a medium, so some type of area of space, some type of molecules, particles to carry that energy through, whilst electromagnetic waves don't require that. It just needs magnetic fields and electric fields propagating themselves. So a type of example, mechanical wave is sound. So mechanical waves require particles. You could say it requires a medium. Whereas this is just changing electric fields and changing magnetic fields. Those are the things that are required. Okay? Medium, no medium. But at the end of the day, they all have the same type of characteristic. A wave will always refract, reflect, diffract, and superposition. So that's how everything is coming together in this particular module. In Module 4, we talked about magnetic waves and light behavior. In this module, we're talking about sound, but we'll still see the same types of behaviors in sound as we did in light, because they're all, at the end of the day, waves. Okay, so today we're going to look at a couple of characteristics of sound waves. The main thing is looking at the difference between pitch and loudness. How do we differentiate? If you want, you can have some supplementary notes via our textbook. As you would know, hopefully you'll have it at home. So that's the number of pages that you can look at now. Just before we start, you can pause this video at this point here as I go through the multiple choice questions. So first question is the part of sound wave where the characteristics are spread apart. So here we have a longitudinal wave. Remember, sound is actually a longitudinal wave. This component here, it's saying, what's this region here? The answer is B, rarefaction. So that's where we have the lowest pressure. B, it says, in which medium does sound travel fastest in? The answer here is solids. The reason being it's denser. And also, that means that collision between particles is increased. Okay, so like I said, sound is a longitudinal wave. That means these particles will move backwards and forwards in the same direction as the wave is moving. So as, let's say with this diagram here, assuming that my wave is moving in this direction, then throughout the entire space in which that energy is moving, the wave is moving backwards and forwards. So this particle here, let's use this particle here as an example, it can move over here, then back over here. Its net displacement will still be the same, so it'll still be in that relative position overall, but it will be moving backwards and forwards. How could we visualize sound? If some of you remember, there was a little video I showed before where we use a tuning fork and we put it in a beaker of water. That's one way. You could also use a tuning fork and place it near a flame after obviously you've given it a little whack. And you can see the vibration on the tuning fork affecting the motion of the flame, or you can see it producing a nice little splatter of water from the water beaker. Other ways you can do it is obviously some audio frequency generators, loudspeakers, oscilloscopes, and electrical signal, which we're going to try and do with a little simulation to get ourselves started. Now, if we kind of look at the behavior of sound waves, we firstly talked about reflection. So again, it follows the same idea with Snell's law, the concept that the incident angle will equal to the reflection angle. So incident is equal to theta reflection. Its application is found in ultrasound, as you can see here in ultrasound. Now the way it works tends to be, at least what I was explained to, is the white matter that you see, or the more white matter you see, that's sort of more solid the matter, so that's more body tissue. The darker the screening that you see here, that has to do with the fact that it's more liquid-based substance that's being observed. We have interference that works with sound, so noise cancelling headphones. The way it tends to work is when the sound outside of you is generating a specific wavelength or frequency, your headphones is designed to detect the movement of the sound, and it's going to create a wave that's coming out in the opposite direction to superimpose against it, so they kind of cancel each other out. So that's how noise cancelling headphones work. This cancelling out, we call that destructive interference. And also diffraction of sound, so bending of waves in between. One of the examples we used is in the highways, they tend to have sound barriers that actually blocks off the shorter wavelengths, so the really high-pitched noises from coming through the actual wall into residential areas. As you would know, the higher the frequency of the sound tends to damage your hearing a lot faster as well. Okay, so the first thing we're going to try and do is show the characteristics between pitch and loudness of a sound wave. So this is going to be a little simulation. I'll put the links in the comments below as well, so you can access. It will require a Flash app. You can just download that. So we have sort of an electronic piano connected into, this is what we actually call an oscilloscope. Actually, based on the signaling that you generate, it will give you a nice little sine wave of sorts there with the setting that we have. Obviously, longitudinal waves shouldn't give these kind of transverse shapes, but if we convert the sound waves into an electronic or electric pulse, then obviously we can convert it into a transverse wave of our choice. So what we're looking at here is two things. We're trying to look at the characteristic of pitch. So what component of a wave will tell us its pitch? So how high it is, how low it is, and also how loud. How do we know the volume? What feature of the wave can tell us that? So I want you to quickly pause this video, just have a read of these questions. Exact same idea of what we talked about just then. We're going to try and look at what difference does it make in terms of the wave to see a higher, lower pitch or a higher and lower volume. Okay, so I'm going to access this simulation now. Okay, so this is the one we have here. Okay, so to do this, I will have to show you the settings. So I prefer you to use the settings at 1 and 1 here. So the first one here gives you the movement vertical. This one gives you the movement horizontal. And you can actually hear the different types of sounds you generate as well. So I'm just going to turn off my headphones just so that can be recorded through. So as you can actually see from what we did there, hopefully you heard the sound recording, but volume if volume is changed, you can actually see the structure of our wave is taller. So the amplitude increases with a higher volume. If I take the volume really low, the amplitude is also very low. Frequency, however, changes the overall pitch. And you tell the pitch is getting higher because the wavelengths are getting shorter. So frequency affects the pitch, volume or amplitude of the wave will affect the volume of the sound. Okay, so that's our kind of conclusion here. If we have a higher amplitude, that will lead to a higher volume. If we have a lower amplitude, we have a lower volume. So this affects volume, whilst frequency affects our pitch. Okay, now why is that the case? Now if we kind of look at the relationship between frequency and period, and then remember period is how long it takes to generate one wavelength. Another way of seeing frequency is it's just a measurement of how many waves for a specific point in time. And that's consistent with the formula up here. This is the time it takes for one wavelength. Okay, so this is for, let's say, period is for one lambda, one wavelength. Now if we don't know what the actual period is, we could still count the number of compressions or refactions, and then the time it takes to record all those different values to come up with a value for frequency. So that's another way of doing it. What we do also know is if we have a higher frequency, that leads to, based on our formula, higher frequency leads to a lower wavelength, assuming that obviously the wave is traveling at a constant speed, which it should, given the type of medium it's traveling through, which means that frequency and wavelength are inversely proportional to each other. So that kind of explains why when we generate a high pitched sound, the wavelength of that sound actually gets smaller. Okay, and that's the same idea if we're looking into electromagnetic waves and light as well. Okay, so this is just something for you to copy down. Frequency, obviously given in hertz, it should be lowercase z, named after a guy called Heinrich Hertz. He's famous for discovering radio waves. N, number of wavelengths that you see, compressions, refactions, really depends on the question. Time taken, obviously time is always given in seconds. Okay, the main point you need to remember is the volume, or what we say the loudness, is related to amplitude, and frequency is related to the pitch. And if some of you don't remember what the amplitude is, it's the displacement of the wave vertical to the axis. So this particular axis that we have here this point to this point, that's your amplitude there. Okay, so let's just go through the multiple choice. Again, you can pause it here just so you can give yourself a go, but we'll explain the question in 3, 2, 1. So the number of compressions which pass a certain point in 1 second, which characteristic best describes this behavior? Obviously, in this case, it would be frequency. Okay, because the fundamental formula for frequency we just talked about. Frequency, number of compressions over time. The sound of a tortoise walking is much more quiet than a nearby explosion. What can we infer about the sound waves produced? So if it's a lower volume, it means a lower amplitude. So B. Okay, now here's a little interesting diagram to kind of show you the kind of ranges that we can listen to. Now, the average human, from the little research I've done, the average human should be able to hear a range of about 20 hertz to about 20,000 hertz. Okay, you'll see some Hollywood movies where they do the dog whistle blowing and you don't hear any sound, and then you have a pack of dogs coming by. The reason being is those dog whistles are a much higher pitch. Now, what essentially that means is if you can generate a sound that is outside both sides of our ranges, so maybe the range is really low or maybe the range is really high, then the human ear cannot detect it, or at least we don't register it. As you grow older, what generally happens is you tend to lose a bit of the range in the higher frequency area. Now, I know from my own experience in high school, some of my mates would used to generate those signals at really high pitches, and that would annoy quite a lot of people in class. But our teacher didn't hear it because they basically lost the ability to register this really high pitch sound. Now, I hope this never happens to me, so, don't feel too foolish in the room when someone does that. But that's kind of what happens. You tend to lose the higher frequency ranges first as you age, because that's the first thing that gets damaged due to the hair, the sort of detectors that's inside your ears. Next, we're going to try and visualize sound. Now, sound is a longitudinal wave, so the best way to demonstrate that is actually through a thing called a Reubens tube. Obviously, I don't have a Reubens tube to show you, so we're going to just have to go by videos and also through some little nifty animations. Now, we know that sound is a longitudinal wave, so it's going to come backwards and forwards as we produce sounds. Now, with a Reubens tube, if you put in a bit of gas from the Bunsen burner and then light it all up, you get this nice little shape here. Okay, so these points here, I might just change the color. These points here, these maximum points, we call these antinodes. So the antinode, where we get antinodes, we get max volume of the idea. You can actually go online and use a sound generator to find this out here. If you use a signal generator, where you're standing on the antinode, you actually experience a higher volume of the signal. And then we have these bits here. I might change the color so no confusion. So I'll use these ones down here. These are nodes, and this should be the lowest volume possible. Alright, theoretically speaking, there should be no volume, or close to nothing. So that's what we have. So if you make a signal, a standard frequency signal, you should find points where it's really high in volume and where it's really low in volume. Now, the reason why you have these antinodes and nodes, that's to do with the compressions of the waves. So where the waves are compressed the most, you'll get your antinodes. So the maximum compression points, that's where you get your antinodes. the place where the molecules are sort of moving away from each other, and it's really really less dense. It's kind of trippy. So where it's really not really dense at all, that's where you get the nodes, and that's where you get no volume or low volume. So that's kind of what we represent here. Same idea here if we actually look at this little sketch. As you can see, this is actually just a simulation of a sound speaker. So when a speaker generates sound, it goes in all directions, and that works with all waves. As you can see, there are compression points. The reason why it's spreading out is because these particles are colliding with other particles around it, and it's transferring energy. So what's happening here is the speaker, once it generates these vibrations, that energy is being transferred through these collisions, and it's being transferred all the way outwards. Same idea with the Reubens tube. We can actually visualize sound as well. So let's try and show this one as well. All right, here we go. So if we actually have a look, if I increase the loudness, this time I won't play the audio, but if I try and increase the loudness, you can see what actually happens to the movements of our particles, and I'll show this particular molecule's movement. So if I increase loudness, you can see that. If I go to really loud, so maximum volume, you can see sort of change there. So as you can see, it doesn't appear to be a massive difference. You can see with loudness, it does affect our overall amplitude. So you can see the displacements are sort of longer here with loudness. If we change the pitch, you can see also these are a lot closer to each other. Okay, so this is sort of representing or visualizing sound in a medium here. So higher pitch, you can see the movement is a lot closer. Lower pitch, you can see it's a lot more spread out. You can also see it in the summary here. Try it again with the loudness. So that's our motion, and then we go to really loud. You can see there's a slight increase in the displacement as well. Okay, so there's that. Alright, so a couple of questions I want you to go through. Calculating the frequency. So I'll just go through the answers here. The first one, the important part is you got to convert your units into the correct SI units. So 3 centimeters, convert that into meters. Simple way of doing that is to do it 10 times to the minus 2, or in this case actually the time period, 3 times 5. So if you actually look at the units here, the actual distance, the wavelength we have here, and the time period, that's milliseconds. So what we can actually do is just by timesing that, the centimeter signs will cancel each other out, and that'll give us 15 milliseconds, which can be converted into 0.015 seconds. To find frequency, 1 over 0.015, 67 hertz. Okay, so that's how you do a question like this. You can just simply look at the units to work it out there. Same type of question here, so I won't go through it again. Okay, so if we kind of look at in terms of the variations in air pressure, which we showed just then, we can see that where there is low or big displacement of particles, so they're really far apart, that's where we get low pressure, and obviously where the displacement is very low, we get really high pressure. Okay, so this is what we can see here. So the smaller the displacement of the particles, that's the greater compression or highest compression point, and the bigger the displacement particles are from each other, we have really low pressure and hence a rarefaction. Okay, so that's for you to copy down. Alright, the last little bit we have is just a little calculation question, so just go through this one. And don't want to dwell too much on the content. So we have 30 compressions, so n is equal to 30. We have a time period of 0.1 seconds. So the frequency we have is n over t, 30 over 0.1. And next question we need to find is the amount of compressions. So we want to know what n is. We know that frequency is 600, and we also know that time is 0.05. So the standard way of doing it, at least in New South Wales, is they do encourage you to try and substitute in the values first before you do any rearrangements, because you do get marks for correct substitution. Okay, so 600 times 0.05, and that's the number of compressions we have. We can do also is obviously calculate the values. Now, one thing to take into account is obviously significant figures do take into consideration the lowest significant values given to you in an equation, and that's how many significant figures you need to produce. So the first one, the lowest sig figs is 3, so make sure this is in 3 sig figs. And then in our second one we have here, it is 2 sig figs we need to take into account. So this would be about 30 compressions. Okay, and that's how you do the question. Alright, so just to end ourselves off with our little summary, we already talked about today, we talked about the sound and how pitch and frequency affect sound. We said that high pitch, high frequency, higher amplitude leads to high volume. That's what we got. We also looked at how to model a longitudinal wave like sound. We know that when there is higher pressure, that's a compression, and lower pressure, we have rarefaction. So that concludes us for this particular dot point and inquiry. Feel free to always come back to the classroom. There's going to be more videos on sound waves coming up shortly, so until next time, stay safe and study hard.